Assalamu alaikum, everyone. Today we have to study ideal gases, and specifically we'll be studying ideal gas equation as part of A2 syllabus of thermal physics. So let's move on to the syllabus content. This is the syllabus content. Um, we have to study uh, equation of state, in which we'll be studying the ideal gas equations like PV is equal to nRT. We'll be looking at number of moles. Then we'll be looking on kinetic theory of gases, specifically for the ideal gas. For that, we have to study on Brownian motion. Then we have to study the basic assumptions of kinetic theory of gases. And then we have to use that to derive a main equation, core equation, which is P, pressure times volume, equal 1 by 3 of nmc square. N is total number of particles of gas, m is mass of one gas particle, and c square is the average mean squared speed. And then we have to derive another expression relating this Boltzmann constant, which is K equals R over NA. And then we have to compare the two equations to get further relation between temperature and kinetic energy. So all this we have to study today. Okay, let's move on to to the assumptions, to kinetic molecular theory assumption. There are 5 basic assumptions for the gases. Number one, the assumption number one is gases consist of very large number of tiny spherical particles that are far apart from one another compared to their size. Its meanings are based on the common sense that the gas consists of too many atoms and molecules, and they're very tiny to be looked upon. We can't see them. And then the distance between the gas particle is much greater than the distance between any other particle in the matter, like liquid or solid. And then obviously most of the volume occupied by the gas will be consisting of the empty spaces, and there will be large empty spaces between the particles. So we say if we combine the volume of all the gas particles and we look over how much volume gas is occupying, then there would be a significant difference between the two. The volume occupied by the gas would be much greater than the total volume of the individual gas particles. Okay, the second is gas particles are in constant rapid motion in all direction. This is a common sense thing again, that the gas particles are fastly moving and they're having greater kinetic energies. And we know that kinetic energy is because of their motion. So the particle will be moving along straight line unless they encounter any other particle or the walls in their way, and then they change their position. Third one is collision between gas particles and between between gas particles and between the container walls are elastic. So elastic collision in one, there is no loss of kinetic energy. So for ideal gas, it is assumed that the particles are colliding with each other and with the walls elastically. So during collision, there is no other energy that is being produced. So the total kinetic energy remains the same. So there are no forces of attraction or repulsion between the gas particle. So for ideal gas, we assume that there are no forces, there are no bonding, or there are no intermolecular forces at all. So we say that there is no molecular potential energy. It means the internal energy of the gas particle is completely because of its kinetic energy. Number 5 is the average kinetic energy of gas particle is dependent upon the temperature of the gas. So it's again a common sense thing. Whenever you heat up something, its temperature is raised, then the speed of particle will be increased. As a result, this will change the kinetic energy of particles. So one more thing, that in a gas, there are millions and trillions of particles. So not all of them would be having the same speed and same kinetic energy, but we take their average. So we say that the temperature of the gas is proportional to average kinetic energy of the gas molecule. It's not dependent upon single kinetic energy of the particle, but it depends upon the average kinetic energy. So these were the 5 points. Let's move forward and let's look upon ideal gas equation. Before we look at the ideal gas equation, let's look what is the ideal gas. Ideal gas is a gas which obeys all the laws, which obeys all the gas laws without any restriction in condition of like pressure, volume, and temperature. So for ideal gas equation, we have to derive several of the equation. Let's say the first equation we will look for will be PV is equal to nRT. So what's that? The ideal gas law is the equation of state of hypothetical ideal gas. It is a good approximation for the behavior of many gases under many conditions, although it has several limitations. The real gases have several limitations, like Boyle's law, you have to keep temperature constant. For Charles' law, you have to keep pressure constant. And for Gay-Lussac's law, the pressure temperature law, you have to keep the volume constant. But for the ideal gas equation, you don't have any restriction of these conditions. So PV is equal to nRT is the first gas equation, where P is the pressure of the ideal gas, V is the volume of the ideal gas, N is the amount of gas measured in moles, R is the universal gas constant, T is the thermodynamic temperature. And then the statement, the product of pressure and volume of the gas bears a constant relation with the product of universal gas constant and the temperature. So PV proportional to RT. And then you introduce the constant, which is N. So PV is equal to nRT is the first equation. Let's move on to studying what is universal gas constant. So like when the molar mass of any gas is multiplied with the specific gas constant R, it is observed that product R is always the same for all gases. This product is known as universal gas constant. This is the definition of R. And you know the value of R is 8.31 joule per mole per Kelvin. This is the value for R. Okay. Well, when we have to derive the equation, again, the same equation that we studied before, PV is equal to nRT, it's quite obvious that we have to assume that let's consider the pressure exerted by the gas is P, the volume is V, the temperature is T, and N be the number of moles of the gas, R is the universal gas constant. So according to Boyle's law, we have the relation that the volume is inversely proportional to pressure. And secondly, according to Charles' law, volume directly proportional to temperature. And the third law is that volume of the gas is directly proportional to number of moles. So greater the number of moles, the number of particles, greater would be the volume. So when you combine all of these together, so you will get V proportional to N T over P, right? Combining all of them and then taking P on the other side. So PV proportional to NT and then introducing a constant over there. So the constant is R. So you say P is R and T. So when you rearrange that, it will be P equals nRT. So that's how you derive this equation. Okay, let's move on to another equation, the second equation, like the second ideal gas equation. And the second ideal gas equation is PV is capital N K T. So since we know one thing, that PV is N R T, and we know one thing as well for the number of moles, that is equivalent to total number of particles over Avogadro's number. So when you replace this over there, so that will be like PV is N over NART. And then again, you will reassemble that. So it will be R over NA into T. And beta, this R over NA is known as K, which is Boltzmann constant. So that's how you derive that, where K is Boltzmann constant. And again, it's a constant that's having the fixed value, and its value would be usually given in the data booklet. Okay, so this is the second equation. Okay, let's move on towards the third equation. The third equation is we have to derive PV is 1 by 3 rho C square, or it can be P is 1 by 3 Nm by V C square. So this is the main equation we have to derive today. Okay, so this rho is the density of gas, and this is mean squared speed. Mean squared speed of gas particles. And beta over here, the N is total number of particles. Total number of particles. And this M is mass of one particle. Mass of one gas particle. And this V is total volume of gas. Total volume of gas. So that's how we have to derive this expression. Okay, so let's first make a box, cubic box, in which gas particles are there. So let me make the cubic box first. Let's say this is the box in which the gas particles are there. This is x-axis, this is y-axis, and this is z-axis. So let's say there are too many gas particles which are moving randomly in this container. So too many gas particles are all over there. So these are gas particles. Okay, we have to consider any one of them. Let me consider this gas particle, and let's say it is moving this way with a speed cx. Okay, so if we consider one gas particle, then obviously it is moving along three axes. Let's say this is x-axis, this is y-axis, and this is z-axis. So if it is moving with c with speed c over there, so its component along x-axis would be cx, its component would be along y-axis would be cy, and its component along z-axis would be cz. And then applying Pythagoras theorem on three dimensions, the c square will be equivalent to cx square plus cy square plus cz square. So that's how we can express the speed. This is purely according to the Pythagoras theorem, as you must have studied in the projectile motion, that you dissolve one velocity into two components, ux and uy. But over here, as the gas particle is moving in three dimensions, so we have to dissolve it in three components. So that is c square is the total speed, like the square of the total speed. Cx is the speed along x-axis. So this is along x-axis, and cy is the speed of the particle along y-axis, and cz is the speed of the gas particle along z-axis. So that is your key. Okay, moving forward, beta, you know that let's consider that this particle, if this particle is moving along x-axis, then this is the wall with which the particle is going to collide after some time. So this is the wall, and let's assume that this cube is having each side is L. Each side is L, length, width, height is L, right? As it is a cube. So what's going on is that let's say this gas particle is going to hit this wall. Let's say this is the wall, and this is the particle, and it is moving along x-axis, so its component is cx. So we are taking motion of gas particle along x-axis only. So when it is going to hit the wall, of course, it is going to exert a force on it, and then it is going to exert a pressure. So we know that the gas pressure is equivalent to force over area. So let's first look upon the force, how much force it will exert during the collision. So we know that force is equal to change in momentum over time. And the change in momentum of gas particle would be 2mcx over t. Why it is 2mcx? Because look, change in momentum is mv minus mu. So let's suppose that once it collided and it moved back with this speed, with the same speed cx. So let's take the original velocity negative and the recoiled velocity positive. You can take the other way around as well. That will only introduce the negative sign with 2mcx. So it is mcx minus m minus cx. So it will be 2mcx. That's why I have written it over there. And for time beta, like this t, let's look upon t. If you want to find value of t, it is the time for next collision of gas particle with the wall. Next collision with wall. So for this, we assume that the gas particles are moving with constant speed because the temperature is constant. And then let's say this is the one wall and this is the second wall. So if a gas particle started its motion from this wall, it is moving to the other wall. So it has covered a distance of L. It collided and then it comes back. So for the same collision with the wall, it has to move this distance twice. So we say V is distance over T and T is distance over V. And then T is 2L by CX. 2L because it has to cover at least 2L distance to collide the same wall again. And then CX is its speed along x-axis. So what we will be doing is we will be replacing this value of T over here to get the new force value. So let's look upon the new force value. Change in momentum is 2mcx and the time value is 2L over cx. 2L over cx. So 2 goes away and cx will be moved upward. So 2mcx square over L. This is your force expression. And now you have to get back to the main pressure. So you have to insert the force value over there. So we say that since pressure is force over area, so putting the value of force over there gives you mcx square over L into A. And you know L into A is actually the volume. So it is mcx square over volume. So we say that pressure due to one particle is P equal mcx square over V. And pressure due to n particles, pressure due to all particles, like n particles along x-axis only, is P equal nmcx square over V. N is the total number of particles that we have introduced. Okay, this is along only x-axis as well. But now let's look upon a thing. Since we know that c square is cx square plus cy square plus cz square. And as temperature of the gas is constant, so we assume that all the components cx, cy, and cz are equal to each other. They are equal to each other. So, replacing cy and cz in above equation, like this equation, with cx. So replace that with cx. So it will be all would be cx because all the components are equal. So you can replace that. So you will get like c square is 3cx square. And from there, cx square is c square by 3. And you can introduce this sign as well because this is the average. This is the average speed because you're taking for all the components. So c square is mean squared speed of gas particles. So now what you will be doing is you will be replacing this in the previous value over here with Cx. So you have to replace it. So P equals nmcx square by 3. So replacing this Cx, you will get the new equation as P equal nmc square and it would be volume over there over 3V. So then when you rearrange it, it will be P equal 1 by 3 Nm by V C square. So this is the required equation that you need, and you can replace this with density as well. So pressure is 1 by 3 density C square. So that was our required derivation. Okay, moving along, we have to look for another derivation, which is kinetic energy versus temperature. So this is again a very simple derivation. We know that PV is nKT, and we also have derived that PV is 1 by 3 nmc square. We just have derived this. It was P equal 1 over 3 Nm over V, but I took V to the other side. So now you can see that as both of them are the product of pressure and volume, which will remain the same. So it means that there are these values nKT and this 1 by 3 nmc square, these would be equal to each other as well. So comparing them, comparing these two, we can say that nKT is 1 by 3 nmc square. And then shifting 3 to the other side, it is like, okay, n would be cancelled away from here because n is the total number of particles. So it will be like 3 kT equal mc square. Okay, now what you have to do is you have to multiply both sides with 1 by 2, because only then you will get 1 by 2 mc square, which will be equivalent to mean kinetic energy or average kinetic energy. So this is known as average kinetic energy. And over here, it will be 3 by 2 kT. So that's why we can say that average kinetic energy is equivalent to 3 by 2 kT. This is the derivation. And for kinetic energy, it is 1 by 2 mc square equal 3 by 2 kT. T by 2 kT. So over here, we can see that 1 by 2 m is constant and 3 by 2 and k is also constant. So we can say that mean square speed proportional to temperature. Our temperature is proportional to mean square speed of the gas particles. So just talking about the equations over here, the first equation is the Boyle's law, like PV is constant. So you can do P1, V1 is P2, V2. The second equation is the Charles law, which is V over T is constant. So it is V1 over T1 equal V2 over T2. The third equation is Gay-Lussac's law or pressure temperature law, and that is like P1 over T1 equal P2 over T2. And then coming about to the moles, so moles is total number of particles over Avogadro's number. Mole is mass in gram over molar mass. And then for the ideal gas equation, PV is nRT, or PV is capital NKT, or PV is 1 by 3 NMC square. And the final one was average kinetic energy of the gas particle is equivalent to 3 by 2 kT. So these are the equations which are useful in ideal gases. So I hope that this thing is clear. Now our syllabus is completed. Congratulations to all of you. And I hope that these things must have made sense for you to understand them. I will suggest you to go through them today and start solving the past papers for the ideal gas, because this ideal gas is the most important topic for the current mock. Thank you very much, students. Take care.